Hello and welcome. In this video, we will talk about indirect proof and we will discuss two methods, that is contrapositive and the contradiction. As we talked in previous video, there are two types of proofs, direct proof and indirect proof. In direct proof, we are trying to prove conclusion from the premise, that is our statement would be of the form if P then Q. And for all the true values of P, we are trying to prove that Q is also true. Whereas in case of indirect proof, we have two types, contrapositive and contradiction. In contrapositive, we are simply negating the truth value of statement, and we are interchanging the sign between premise and conclusion. So we are trying to prove that if conclusion is not true, then premise is also not true. Okay? Or if conclusion is true, then premise is true. That is what contrapositive is. Whereas in contradiction, we are starting with the wrong assumption that whatever statement is given, that statement is false. And then subsequently, we will try to prove that our assumption itself is false and hence the original statement is true. Proof by contrapositive. The contrapositive of a conditional statement is formed by negating both the terms and reversing the direction of inference. So our original inference was P implies Q. That becomes negation Q implies negation P, and that is true. So if this is true, we can say that the given statement, original statement, is also true. A statement and its contrapositive are logically equivalent. That means P implies Q is same as not Q implies not P. So we are given proposition if P then Q, then we are starting with negation of the conclusion part, that is we are assuming that negation Q is true, and from that through the step-by-step derivation we prove that okay, negation Q implies negation P. Let us try to understand it with the example. Prove that if I into j is equal to n, then I less than or equal to root n or j is less than or equal to root n. Red part is our premise and the blue part is our conclusion. So now we will start with the wrong conclusion. So our P is I into j is equal to n. So the negation of that would be I into j is not equal to n. And our Q is I less than or equal to root n or j less than or equal to root n. So negation of Q would become I is greater than root n or j is greater than root n. As I discussed that contrapositive start with negation Q, okay, and we will try to prove that from negation Q, negation P is derivable. Here, our negation Q is having two parts. One is I greater than root n. If we multiply on both the side by j, then we will have I into j, which is greater than j into root n. Right? Let us call it as equation number 1. The another part of conclusion is j greater than root n. Again we will multiply, if we multiply it by root n on both the side, then this would become j into root n greater than root n to root n, that is n itself. Let's call it as equation number 2. So from equation 1 and equation 2, if we apply the property of transitivity, because I into j is greater than j into root n and j into root n is greater than n, so directly it implies that I into j is greater than n, right? I into j is greater than j into root n and j into root n is greater than n. So it is a property of transitivity which says that I into j is definitely greater than root n, and hence it is negation P. And as you can see that it implies that I into j is not equal to P. I into j is not equal to n, and that is what our negation P is. Hence, we can say that given proposition I into j is equal to n, then I less than or equal to root n or j less than or equal to root n is true, or this is proved. Let us take one more example. For x belongs to z, if 7x plus 9 is even, then x is odd. So again we will prove it using the contrapositive method. Here P is 7x plus 9 is even. So the negation of that would be 7x plus 9 is not even. And the conclusion Q is x is odd. So negation of that would be x is not odd. We will always start with negation x and we will prove the negation P, because this we have to prove. So our conclusion is x is odd. So we'll start with negation. So that will be x is not odd. That means x is even. So if x is even, we can assume that x is equal to sum 2a, where a could be any value from that capital Z. When we multiply any number by 2, it definitely becomes even. So now x is even, x is equal to 2a. 7x plus 9, we can rewrite it as a 7 into 2a plus 9. We assume that x is 2a. Right? So that would be 14a plus 9. 9 we are rewriting by factoring it into 8 plus 1. So that will be 14a plus 8 plus 1. From first two term, we can take 2 common because both are even. So we can rewrite it as a 2 into 7a plus 4 plus 1. And 7a plus 4 might be odd, might be even, we don't know. Right? So we'll assume that that number is sum m. So that is equivalent to 2m plus 1. But 2m would be definitely even because it is multiple of 2. And even plus 1 will be definitely odd. So we can say that ultimately 7x plus 9 is odd. And that is what we wanted to prove. That is what our negation P is, that 7x plus 9 is not even. Hence, it is proved that a given statement, that is if 7x plus 9 is even, then x is odd. We can say it would be always true. Proof by contradiction. To prove something by contradiction, we assume that what we want to prove is not true and then show that the consequences of this are not possible. We won't be able to derive that statement and hence our assumption is wrong. So the given statement is true. It establishes the truth or the validity of a proposition by showing that assuming the proposition to be false leads to the contradiction and hence our assumption itself is wrong. Using contradiction, prove that root 2 is irrational number. So we'll start with the wrong assumption that root 2 is rational number. If root 2 is rational number, we should be able to write it as a factor p by q. Right? Taking square on both the side, we will get 2 is equal to p square plus q square and p square is equal to 2q square. As p square is equal to 2q square, p would be definitely even because square of all even number is even. For example, 2 square is 4, which is even. 4 square is 16, that is even. 6 square is 36, it is even. So square of any even number would be always even. And p square is equal to 2q square. That ensures that 2q square is definitely even because it is multiple of 2. So p is even. So we can assume p is equal to sum 2k because when we multiply k by 2, that will also become even. So we can always consider p as a 2k. So we can rewrite p square is equal to 2q square as 2k square is equal to 2q square. That would be 4k square is equal to 2q square. And that implies q square is equal to 2k square. So again, q square is 2k square. So we can say q square is also even. So q is also having some common factor 2. So thus p and q both are even number because both are multiple of 2 when we take the square of that. So they have common factor which contradicts our assumption. Right? P is also even, q is also even, and we assume that root 2 is equal to p by q. We have assumed that it is a rational number. So if it is a rational number, there should not be any common factor in p and q, but now we have proved that both are even and hence 2 would be common in both. Okay, 2 will be one of the factor of p and q and that will lead to the contradiction that no, our assumption is wrong and hence it is proved that root 2 is irrational number. Consider another example that prove that root 3 is irrational number. So start with the contradiction of the statement that assume that root 3 is a rational number. Right? So we can say that root 3 is equal to p by q. Take the square on both the sides. So 3 is equal to p square by q square. That implies p square is equal to 3q square. So p is divisible by 3 because p square is multiple of 3q square. You consider the square of any number which is multiple of 3 would be definitely multiple of 3 itself. So 3 is multiple of 3. Its square is 9. It is also multiple of 3. 6 is multiple of 3. Its square is 36, which is also multiple of 3. 9 is a multiple of 3. Its square is 81. That is also multiple of 3. So it is proved that if any number is multiple of 3, then its square is also multiple of 3, or vice versa. If square is multiple of 3, then its square root is also multiple of 3. So we have p square is equal to 3q square. So square of p is multiple of 3, fine, because it is 3 into q square. So we can assume that p is equal to 3k because p is also multiple of 3. Let us replace this value. So we will have 3k square is equal to 3q square. That would be 9k square is equal to 3q square. And hence we can say q square is equal to 3k square. So for the same reason stated earlier, q is also multiple of 3. Okay? It is also divisible by 3. And thus p and q both have common factor. And hence whatever assumption we have made that root 3 is rational number contradicts with our proof, and hence we have proved that our assumption is wrong, and hence given statement that root 3 is irrational number has been proved. Prove P union Q is equal to Q union P. So let us start with the contradiction, that we will assume that P union Q is not same as Q union P. Let X belongs to P or X belongs to Q. So we can say that X belongs to either P or Q. Right? That is obviously because that is what the definition of union says, that if X is in either of the set, then it is definitely member of union of it. From the definition of union, it is implies that X belongs to Q union P as well, because we know that set is having the property of commutativity. Okay, so P union Q is same as Q union P. So if X is in P union Q, then definitely X would be in Q union P as well. Right? So again, from the definition of union, if X is in P or X is in Q, then definitely X is in P union Q. And from the property of the commutativity of this set, we can say that P union Q is same as Q union P. And if due to that, if X is in P union Q, then definitely Q would be in Q union P as well. And hence our assumption P union Q is not same as Q union P stands false. And hence we have proved through contradiction that P union Q is same as Q union P. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.